Okay, so in this video, what we're going to be doing is reviewing the DC motor practical quiz, because there's a few key things to pick up with that. Okay, so the first thing we have to do is draw a circuit diagram of the setup that I showed you in the video, including the symbol for a motor, which we may have met once in year 9, but we haven't really spent any time looking at them. So your circuit should look like this. We had a DC power supply. I actually had 4 cells in there, but it doesn't matter too much. We have an ammeter that has to be in series if we want to measure the current, and we've got our motor, and then we had a rheostat or our variable resistor. Those were our key parts of the circuit. Okay, so moving on from that, let's actually dig into it a little bit more. So in the setup, we're looking at describing where the North Pole and the South Pole are, and then figuring out the direction of the field. So again, this I just told you in the video which of these two, so as long as you were paying attention, you'd have picked that up. So I told you the North Pole was on the right-hand side, and the South Pole was on the left-hand side, and that means the field lines are going from right to left in here, because they always go from north to south. So if we're using our Fleming's left-hand rule, our index or first finger is going to be pointing from right to left. Now, something I picked up in discussion with a few of you is a few of you had your middle finger and your first finger the wrong way round. So the way to think about this is your first finger should be parallel to arm. So if you point your arm out, you should essentially be able to point at stuff with your index finger, because your arm and your finger will all be in a straight line, and then your middle finger will be at 90 degrees to that, as will your thumb. So that's just checking we've got our index and our middle finger the right way round. Okay, so that is our motor setup there. North Pole right, South Pole left, field lines going from right to left. So let's just quickly put that in. So they're going from right to left because they always go from north to south, and that means our index finger points in that direction. That's our field finger. Okay, so in order to connect the windings of the motor to the DC power supply, we use 2 key parts. One which is directly connected to the power supply, and the other one that's directly connected to the windings. So let's have a look at this. So I've drawn a quick diagram here. So there are 2 parts there. So I've reoriented slightly. So here's our power supply. That is directly connected to these brushes here. So that's what's directly connected to our power supply. Our split ring commutator is connected to the wires. So if we were to add on the motor in here, the actual motor itself is connected directly to the split ring commutator like this. So that's the way round that we need that. So we've got the brass brushes directly connected to the power supply. The copper split ring commutator is directly connected to windings. The material isn't particularly important. That's just what it was in this particular motor that we built. Okay, so what is the role of the split ring commutator in the motor? So we met this when we made our notes on it, but I think it's always worth sticking back in so we remember. So it reverses the current in the windings every 180 degrees of rotation. And the reason we want that is to keep it rotating in the same direction. So that's why we have this commutator brush set up. We want our motor to keep spinning in the same direction. Okay, so we've got our diagram of our DC power supply over here on the left, and we want to know which way the conventional current comes out and which way the electrons come out, and what way that means it's going around our circuit. So let's have a look at it generally, and then we'll have a look at our actual circuit. So if you have a circuit symbol like this, the current comes out of the long side. So when we mark I, we're indicating the direction of conventional current. So that comes out here. Electrons are actually coming out this other side. So it's always in the opposite direction to conventional current. So in our circuit, this was our diagram. The longer side was on the right, so conventional current is coming clockwise around the circuit from the way we're looking at it here. So just in terms of why we have these 2 things, because we now know that a current is a flow of electrons, it's simply because all of these rules with magnetic fields, and actually most of circuitry ones, were discovered before the electron. So at that time, they assumed that electricity was the flow of positive charges. As far as I know, for no good reason whatsoever, they just liked positive rather than negative. But that's why we have this idea of conventional current, is because they thought it was the flow of positive charge around the circuit, and we still use this concept because it doesn't really matter. Okay, so going back to things, so the current comes out the longer side, electrons come out the short side. That means the conventional current is flowing clockwise around our circuit, the way we've drawn that diagram. Okay, so we've got a simplified diagram of our setup. So this is us looking down on our setup as if we're like got a bird's eye view of it. So looking at it here, we had our current coming in on this right-hand side. So our current is going to go from A to B to C to D and then out here. Obviously, we had lots of windings on ours, so it's actually going to make a lot of rotations, but it's still going to go in at A and out at D. Okay, so this is our setup. So we're going to use Fleming's left-hand rule on this right-hand side first of all. So current, or conventional current, is going up the right-hand side, so our middle finger is going to point that way. The field is going from right to left, so our first finger points that way. So your thumb should be pointing straight out at you like mine is in the picture. So the side AB is going to experience a force out of the plane of the page. Okay, so that's what we had over here. So the right-hand side is going from, the current is going from A to B. So we're going to have a force on AB out of the page. So what we'll do is we'll do the same process for side CD. So the current is going down the page, because if you think about it, if our current is going up from A to B, it's got to be then going from C to D to essentially allow it to keep going round. So our field is still going from north to south, so it's still right to left, but our current is now going down, so your thumb is now pointing at your screen. So you're going to get a force into the page on this side. Now, we haven't talked about the sides BC and AD because they're parallel to the field, so they're not going to experience a force, so we don't have to worry about those. So side CD is exactly the force in the opposite direction, so AB is out of the page, CD is into the page. Okay, so suggest 3 ways we can make our motor spin faster. So in terms of this, you either need to increase the accelerating moment or decrease the resistive moment here. Either of those 2 things, you're going to end up making it spin faster. So to increase the accelerating moment, we need to increase the magnetic force. So what we need to do is increase the winding current. We could increase the number of windings, or we could increase the strength of that external magnetic field. Now, some people in this row have a higher current, have a higher potential difference, have a lower resistance windings. All 3 of those things are increasing your current. So you've essentially repeated the same thing 3 times, which is why you'll have only got 1 out of 3 for that. In terms of decreasing the resistive moment, realistically, what we'd have to do is lubricate our axle. So we'd decrease our resistance to rotation. I guess we could do it in a vacuum, but we're not. That's going to be quite expensive to manufacture a vacuum for our motor. So those would be realistically our suggestions. Now, some people suggested increasing the distance of the force from the pivot, which sounds like it could work because it's increasing the moment. However, that would also increase the inertia of our motor, so that actually doesn't work. So it's a good thought, but that actually wouldn't make it spin faster. Okay, so those were our things that we could have to make it spin faster. So then we started looking more in depth at moments and explaining why our motor can start in some places and not in others. So just to recap about moments. So a moment of a force is the force times the perpendicular distance. And it is important that it's the perpendicular distance to the pivot. So because on the right hand side the force is up, the distance has to be across from left to right because that's perpendicular to the force. Same thing for this downward force. It has to be from left to right, so it's perpendicular to that force. And our pivot is where the axle is in the middle. So we've now got like a side-on view of our motor. And so that's what we need in here. So we're going to multiply the force by the perpendicular distance between the force and the pivot. So now we're going to explain why our motor will start spinning if it's horizontal, like it is on the right-hand side, and where it won't if it's on the vertical side. So let's actually have a look at that. So on this right-hand side, you can see there is a perpendicular distance between the force and the pivot in the middle. So there is going to be an anti-clockwise moment from both forces. So both forces are trying to make it rotate anti-clockwise. On this left-hand side, although the force isn't applied on the pivot, its perpendicular distance to the pivot is 0 because it's in line with it. So we get a distance of 0, so the moment is 0 here. So if we go back to our diagram, so when the rotor is vertical, the moment of the force is 0, so the force isn't 0, but its moment is. And therefore the motor does not rotate, or doesn't start to rotate. When it's horizontal, the moment of the magnetic force is non-zero and it's anti-clockwise. Oh, didn't want to accept that one. And therefore the motor starts to rotate anti-clockwise. So a few people got correctly in here, said the moment was anti-clockwise and then put it rotates clockwise, which is a bit odd, but that's what we should have in there. It's going to rotate anti-clockwise. So explain why when the rotor is vertical, there's actually no force on it. So a lot of people here actually answered the wrong question. A lot of people explained why there was no moment, not why there is no force. So this was right at the end of the video. So when the motor is vertical, the brushes are actually in contact with the gap in our split ring commutator. So that means there's no current in the rotor windings, so the windings don't have a magnetic field. So therefore there's nothing to interact with the external field, so there's no force. So actually when the rotor is vertical, not only is the moment 0, but actually the force is 0 too, because you're actually disconnected at this point. Then final question I put in here, so if the moment on the rotor is 0 when it's vertical, why does the motor not stop when it reaches this position? Now I got a lot of interesting answers for this one, but the actual answer here is there's actually nothing to explain. Because in physics, you don't need to explain why something continues what it's doing. Everything, if you don't do something to it, will continue doing what it was doing before. So the motor will continue to spin at exactly the same speed unless there is a resultant moment causing that rotational speed to increase or decrease. Okay, so we actually don't need to explain anything here. If it's already spinning, which it is, it will keep spinning because that's what everything does. It just keeps doing what it's doing unless you apply a force or a moment to it. A few people got the right idea here. They said they didn't need a moment for it, but then they said that's because it has momentum. And again, no, not really. Momentum doesn't cause anything. So if we're trying to explain why something happens, we're not going to use momentum because momentum doesn't cause things. The only thing in physics that causes things to happen are forces and maybe the moments of those forces. But momentum doesn't apply here. But we'll explain more about what momentum is in next year when we look at it in more detail.